Hey everybody, in this next video lesson, we're going to talk about something called molecular bonding. Now with molecular bonding, what you're looking at is when you've got a nonmetal bonded to another nonmetal. So you're looking at elements from the right side of the periodic table. This is your carbon, your nitrogen, your oxygen, your sulfur. But also don't forget about hydrogen. Hydrogen is a nonmetal, but it's listed over there with the metals on the left side of the periodic table. But let's not forget about it. Some examples of some molecular bonded molecules include methane and ethane, hydrogen, ethanol, and methanol, as you can see in this picture right here. And these are all nonmetals bonded to other nonmetals. Now, what's different between molecular bonding compared to ionic bonding is that it's not a transfer of electrons like ionic bonding, where one element, the metal, gives its electrons to the nonmetal and they're held together by their opposite charge attractions. But in this case, they're going to obtain a stable electron configuration by sharing their electrons in their valence orbitals. And so some elements will give their electrons to the other element, where the other element will give its electrons to the original element. And between the two of them, they will share electrons in order to achieve a stable electron configuration in what is known as a covalent bond. Remember, nonmetals typically have high electronegativity values, and both of them are going to want to pull on the bonded electrons. And so one's not giving up to the other. They're both sharing. And sometimes it's a sharing that is unequal, but they're both trying to pull at those bonded electrons because of their high electronegativities. Now, this isn't a new topic for you. You've probably learned about covalent bonding in a previous science course, but I'm just reviewing how covalent bonds represent electrons being shared, whereas ionic bonds represent electrons being transferred. Now, I use this term already, but we call packages of elements that are covalently bonded together molecules. We do not use molecules for ionically bonded substances. We call those compounds, but molecules specifically refer to covalently bonded substances. And because of that, they do not form crystal lattices, where a crystal lattice has nice sharp corners and flat sides, and they're very, very high in energy in order to break those bonds. And we'll talk about the bond energy of covalent bonds here shortly. But they do not form crystal lattices. They don't form repeating structures of crystals. Instead, they form irregularly shaped crystals. They'll still form crystals, but they won't be nice and neatly shaped as maybe ionic substances might be. And these crystals that form from molecularly bonded or covalently bonded substances are held together not by positive and negative attractions like the ionic bond does, which as a result forms the crystal lattices. Instead, they're held together by these intermolecular forces, which we talked about earlier in the year. Those intermolecular forces are weak, and they attract molecules of covalently bonded substances to molecules of other covalently bonded substances. They're weaker than a crystal lattice, but the crystal structure is still there. It's just not as strong. Now, the goal of covalent bonding is to sharing electrons in order to achieve a noble gas configuration, which is the most stable and the lowest energy. And what's interesting is that once the electrons are shared, they actually count towards both elements in order to achieve the full octet. For example, let's take oxygen with its 6 valence electrons, and you take another oxygen with its 6 valence electrons. Now, if you take these 2 electrons on the left oxygen and share them with the oxygen on the right, then the oxygen on the right has 8 valence electrons, right? 6 plus 2 equals 8. That's 8. In other words, it's got S2P6, or the electron configuration for a noble gas. Now, because the one on the left is sharing the electrons with the one on the right, now the one on the right is actually sharing the same 2 electrons with the one on the left. And because they're sharing them equally, then you get a covalent bond. Now, if you share 2 sets of electrons, you got a double covalent bond, like this is an example of O2. But if you just share 1 set of electrons, 1 pair, you get a single bond, which is a solid line, and a triple bond, which is possible, is 3 lines. Now, last chapter, we learned about orbitals, the s orbitals and the p orbitals, and how they reside around the nucleus of an element. Now, the electrons live in those orbitals, and specifically the s, the p, the d, and the f orbitals. They're not all that great for bonding. In fact, they're not really that conducive to bonding, and in order for a bond to form, what happens is the orbitals of the highest energy level, or in other words, the valence orbitals, the s and the p orbitals, actually change shape to create new types of orbitals, which we call hybridized orbitals. So you take the s orbital and the 3 p orbitals and turn them into 4 unique identical orbitals, which we call hybridized orbitals. And now, if you have electrons in these hybridized orbitals, whether it be 1 or 2 or 3 or 4 of these hybridized orbitals in use, then it can explain bonding a lot more easily. So bonds form when these orbitals of one element overlap the hybridized orbitals of another element. And we'll talk about hybridization at much greater detail if you decide to take AP Chemistry in a future chemistry class. But think of this as an oxygen with its electrons residing in these hybridized orbitals now, and another oxygen over here with electrons in its hybridized orbitals. And once those hybridized orbitals come in contact or overlap with another hybridized orbital, in this case it's a double bond, so there's two sets of hybridized orbitals overlapping, then you get a double bond. Now there are some special cases where in fact you can use d orbitals, which will allow you to hybridize up to 6 different locations, and that would result in 6 bonds to the central atom. So the big takeaway here is that orbitals, when elements are by themselves, exist, but when they become bonded to something else, the orbitals change into something called hybridized orbitals. Hybridized orbitals better explain the shapes of molecules, which is something we're going to study in the next module. Now you might be asking yourself, why bonds form? What's the reason behind bonding? Well, the reason for every bond is, well, you might guess it, stability. Take a look at this picture. The electrons are attracted to the nucleus of one element. These are shared electrons. These are electrons that make up a covalent bond. And these two electrons are attracted to this nucleus, but they're also attracted to this nucleus because they're being shared between the two atoms. But the electrons themselves are negatively charged, and so they're going to repel each other. And so there's this delicate balancing act between being attracted to both nuclei, but also being repelled by the other electron. And what results is what is known as the bond length. The shared electrons will represent a bond at a specific length depending on the delicate balance between the attraction to the nuclei and the repulsion between themselves. This balance creates what is known as a bond length, or the length of the bond. And the entire reason that bonding exists is because it's going to create a lower overall energy and increase the stability of the atom. Atoms want to bond to other atoms because it's more stable. If it wasn't more stable, they wouldn't do it. A big observation in this bottom purple box is that creating bonds allows for energy to be released in the environment, sometimes in the form of heat, which might heat up some water or cook some food, or the energy might be released in order to break other bonds. But either way, the energy is always going to be released when a new bond is formed, and that energy release will go somewhere. This is always the case. Energy is released when bonds are formed. So as we talked on the last slide, energy is always released when bonds are formed. That means that energy always needs to go in order to break bonds. In this purple box, energy must be input for bonds to break. It's the energy required to break a covalent bond. This is what is known as bond association energy, or just bond energy. And the larger the bond association energy, the more stable the bond is in a molecule. Now, the bond association energy is directly related to the length of the bond, which we talked about on the last page. A longer bond requires less energy. Basically, like imagine a spaghetti noodle that's been uncooked. The longer the spaghetti noodle is, the easier it is to snap in half. And a single bond is the longest of these spaghetti noodles, where a double bond has a shorter bond length, so it's less long than the single, and because of that, the energy needed to break it is a little bit higher. And a triple bond is the shortest of all types and is the highest. Now I have some actual data down here. This is carbon single bonded to carbon, double bonded, and triple bonded. And as you can see, as you increase the number of bonds, the bond length goes down. But as the bond length goes down, the amount of energy needed to break the bond goes up. So the big thing that I want you to take home from this slide is that the shorter the bonds are, the stronger and more stable, and the more energy needed to break those bonds. Now those last couple of slides were a couple of properties of molecules that we wanted to talk about, which were bond length and bond strength, or bond energy. This is a different property. This is called melting point. And you might be thinking, well, melting point, you're just breaking the bonds between molecules. No, when you break bonds, you create brand new substances. In this case, we're not breaking bonds. We're just breaking the intermolecular forces that exist between molecules. And intermolecular forces are weaker than ionic bonds. And so in this graphic over here, we have a mixture of ionically bonded substances and molecules or covalently bonded substances. And anything that's not a molecule, as you can see, must be ionically bonded. And take a look at these. Their melting point is really, really warm, and their boiling point even higher. Same with magnesium oxide, high melting point, high boiling point, and sodium chloride, high melting point, high boiling point. And so those substances we can cross out here because those are not molecular substances. Those are ionic substances. But all the molecular ones, notice how low the melting points and the boiling points are relative to the ionic, because the lattice of the ionic substances causes strength and much higher energy needed to break those lattice, and as a result, much higher melting and boiling points. Whereas The melting points are simply only going into breaking weaker intermolecular forces, so you don't need as much energy, or in other words, you don't need as high temperature. And the last property we're going to talk about when it comes to molecules is conductivity. And conductivity is the ability to transfer electricity. And molecules do not conduct electricity in any state. If you remember, in the lattice, the ionic lattice breaks, and as a result, you have ions floating around in solution. And those ions can allow electricity to flow, and those are considered electrolytes. Well, molecular substances may dissolve, and when they dissolve, they break their intermolecular forces between the molecules, but because they don't have an ionic charge on them, they do not conduct electricity. So they don't break into individual ions. They may separate into molecules, but the molecules themselves don't conduct electricity the way that ionic substances do. Because when they dissolve, only the intermolecular forces are broken, not a positive-negative attraction between oppositely charged particles. And because of this, they don't conduct because there's no mobile charge that can flow. Electricity needs to be able to flow between the molecules of the solution, and the ions help transfer that electricity. But there's no mobile charge, there's no transfer of the electricity, and so there is no conductivity when molecular substances are dissolved into a solution. Now you might remember that water is a molecule, and you're like, well, I know I can get electrocuted if I stand inside a bathtub and try to curl my hair, or if somebody drops an electronic device into the bathtub while I'm in it, I can get electrocuted. And that is true. But you're not being electrocuted, or hopefully you don't get electrocuted, but you don't get electrocuted because of the water. You get electrocuted because of the stuff dissolved in the water. And if the stuff dissolved in the water is ionic, well, then it's going to conduct electricity. And tap water that comes out of your bathtub or out of your shower, that's got stuff dissolved in it for flavor, for minerals. It's got fluoride in there. And all of those ions are allowing electricity to transfer between the water molecules. So it's not the water that's dangerous here. It's the ions that are dissolved. But the good news is molecules don't conduct electricity when dissolved in water. Well, that takes care of this video lesson. Thanks for watching.